Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the story of Oumuamua, the first confirmed visitor from another star system ever detected passing through our solar system. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable, and when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a gentle reminder that while we talk about distant stars, we're all gathered here in this small shared moment on Earth. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and allow your breathing to slow just a little. Tonight, we're not rushing toward conclusions. We're not trying to prove anything extraordinary. We're simply going to follow a mystery, slowly, patiently, the way astronomers do. In 2017, something slipped quietly into our cosmic neighborhood. It didn't announce itself. It did not glow brightly like a supernova. It didn't crash into a planet. It simply passed through, moving faster than anything bound to our sun should move. By the time we realized what it was already leaving. It was given a Hawaiian name, Oumuamua, a scout, a messenger from afar, and it left behind a question that still lingers in the scientific community today. What was pushing it? Was it a dark comet quietly releasing invisible gas? Was it a fragment of some distant planetary collision? Or was it something entirely unexpected? We'll move gently through the science. We'll explore the competing ideas. We'll look at the future missions that may one day give us clearer answers. And if your mind drifts along the way, that's perfectly fine. Let it wander among the stars. We'll still be here. Let's begin. Not with the object itself, but with something much larger. The quiet motion of our own solar system through the galaxy. Our solar system often feels stable. The sun rises and sets. The planets orbit in predictable paths. The night sky appears calm and fixed. But in truth, nothing about our cosmic home is standing still. The sun, along with all its planets, asteroids, and distant icy debris, is orbiting the center of the Milky Way galaxy. It moves at a speed of about 220 kilometers every second. That is faster than most spacecraft we have ever launched. Faster than the object we're discussing tonight was moving when it finally left our solar system. Yet we do not feel this motion. There is no wind rushing past us, no vibration beneath our feet. The Earth carries us smoothly, like a quiet train gliding through the night. As the sun travels around the galaxy, it does not move through empty space. It passes through regions filled with other stars or gas clouds and the faint gravitational influence of neighboring systems. The distances between stars are enormous, measured in light years, where 1 light year is the distance light travels in a full year, moving at about 300,000 kilometers every second. Even so, gravity does not simply switch off beyond a certain distance. It stretches gently, invisibly, like a web woven through space. Far beyond the orbit of Neptune lies a vast region called the Kuiper Belt, filled with icy bodies and dwarf planets. Beyond that, at distances so great that sunlight becomes little more than a faint glow, lies something even more enormous, the Oort cloud. The Oort cloud is not a solid shell. It is more like a distant swarm, a spherical halo of trillions of icy objects loosely bound to the sun. Some of these objects take tens of thousands, even hundreds of thousands of years to complete a single orbit. They are so far away that if you stood upon one of them, the sun would appear as just another bright star. And as our solar system drifts through the galaxy, nearby stars sometimes pass close enough, within a few light years, to gently disturb this outer cloud. not in a dramatic collision, not in a fiery catastrophe, but with a slow gravitational tug, just enough to alter the path of an icy body. Some of these disturbed objects fall inward, becoming the long-period comets we occasionally see glowing in our skies. Others are nudged in the opposite direction. They are pulled free from the sun's weak outer grip and cast into interstellar space. Over billions of years, this process becomes a quiet exchange. Star systems lose material. They shed comets and fragments into the vast dark between stars. And as they move, they may also capture wandering debris from elsewhere. The galaxy, in this sense, is not a collection of isolated islands. It is more like an ocean. And each star system drifts through it, leaving behind small fragments, picking up others, never entirely separate from the whole. It is within this gentle ancient exchange that Oumuamua likely began its journey. Long before it passed our sun, it may have been orbiting another star. Perhaps it formed close to that star, in the warmer inner regions of a planetary system. Perhaps it was ejected during a violent gravitational interaction, flung outward by a massive planet, the way Jupiter can fling comets outward in our own system. Once freed, it would have travelled alone for millions, perhaps billions of years. No sunlight warming it, no atmosphere brushing against it, just the cold vacuum of interstellar space. And during that immense stretch of time, the solar system continued its own quiet orbit around the galaxy. Our sun moved toward the region of the sky we now associate with the constellation Lyra. From our perspective, many interstellar visitors appear to approach from that direction, not because they originate from the bright star, Vega itself, but because that is roughly the direction in which our solar system is travelling. It is a subtle but important distinction. We are not necessarily being visited by objects from Vega. We are, in a sense, running into them as we move forward. Imagine walking through falling snow. The flakes seem to come toward you, but it is you who are moving through them. By some estimates, countless small interstellar fragments may pass through the outer edges of our solar system every day. Most are too small to detect. Most pass unnoticed beyond the orbit of Neptune. They glide through, their paths slightly bent by the sun's gravity, then continue onward into the dark. But once in a while, one comes closer. Close enough to reflect sunlight. Close enough for our telescopes to notice. And in October of 2017, one such object did exactly that. It did not announce itself with fireworks. It didn't carry a glowing tail. It simply appeared in our surveys moving too fast to belong. And so, without knowing it yet, we had met our first confirmed messenger from another star. If our solar system is drifting through the galaxy like a quiet ship at sea, then it is moving through waters that are far from empty. The space between stars may appear black and silent, but it is not a perfect void. It is filled with faint clouds of gas, distant starlight, and every so often the remnants of shattered worlds. To understand how something like Oumuamua could reach us, it helps to imagine the outermost boundary of our own system not as a wall, but as a loose shoreline. The Oort cloud, that distant halo of icy bodies we spoke about, is only gently held by the sun's gravity. At such immense distances, the sun's pull is weak, like the last stretch of a rubber band pulled almost to its limit. Now imagine another star passing within a few light years. That may sound unimaginably distant, but on galactic scales it is a near encounter. Its gravity does not need to collide with the Oort cloud to affect it. It only needs to tug slightly. Over time, that gentle nudge can change an orbit just enough. Some objects are sent inward. We see them as long-period comets, glowing softly as they approach the sun after tens of thousands of years in darkness. But others are nudged the other way. They gain just enough energy to slip free from the sun's grasp altogether. They drift outward, slowly at first, and then forever. When that happens, the object becomes interstellar. It no longer belongs to any star. And if this process happens here, it must also happen elsewhere. Other stars have their own distant icy reservoirs. Other massive planets shift and scatter debris. Other systems eject fragments into the vast expanse between stars. Over billions of years, this creates a quiet accumulation of wandering bodies. Some may be no larger than a house. Others may be kilometers wide. Most are dark, cold, and nearly impossible to detect unless they pass close to a star. This leads to an astonishing implication. There may be countless interstellar objects drifting through the Milky Way at any given moment. Some estimates suggest that very small ones, perhaps only a few meters across, could pass through the outer solar system regularly, even daily. Not because space is crowded in a human sense, but because time is vast and the galaxy has been trading fragments for billions of years. Most pass far beyond Neptune, too faint and too small to ever be seen. They slip through, their paths gently curved by the sun's gravity, then continue on. It is important to remember that when astronomers say something has a hyperbolic trajectory, they mean that it is moving too fast to remain bound to the sun. Imagine tossing a ball upward. If you throw it gently, gravity pulls it back. If you throw it with just enough speed, it might escape Earth entirely. Interstellar objects arrive already travelling faster than the escape speed of our solar system. They are not visitors who intend to stay. When Oumuamua entered our system, it was travelling at roughly 26 kilometers per second relative to the Sun when far away. As it fell inward toward the Sun, gravity accelerated it, and at its closest approach, it was moving at about 87 kilometers per second. That is 87,000 meters every single second. After rounding the Sun, it began to climb back outward, slowing as gravity pulled against it, but not slowing quite as much as expected. But before we return to that mystery, there is another subtle detail to consider. Many interstellar objects appear to approach from a direction near the constellation Lyra, where the bright star Vega shines. It can be tempting to assume they originate there. But this is a matter of perspective. Our solar system itself is moving in that direction as it orbits the galaxy. So when we encounter interstellar debris, it often appears to come from ahead of us, just as raindrops seem to strike your windshield when you drive forward in a storm. The flakes are not chasing you, you're driving into them. This forward motion explains why Oumuamua appeared to arrive from near Vega. It does not confirm Vega as its birthplace. In fact, tracing an object backward through millions of years is extraordinarily difficult. Stars move, orbits shift, the galaxy itself rotates. Small uncertainties compound over time, like tiny errors in a map that grow larger the farther back you try to retrace your steps. Astronomers have attempted to reconstruct Oumuamua's path, identifying several candidate stars it might have passed near in the distant past. Some are dozens of light years away, but none can be confirmed with certainty. After millions of years in motion, the trail becomes blurred. There is something quietly humbling about this. Oumuamua may have formed before complex life existed on Earth. It may have wandered through interstellar darkness for longer than an hour. Species has existed. It may have crossed regions of space lit only by distant stars, its surface altered slowly by cosmic radiation and micrometeorite impacts, and then, by chance, or by the quiet inevitability of orbital mechanics, it crossed paths with us. This is where another important player enters the story: Jupiter. Within our own solar system, Jupiter acts as a gravitational giant. Its mass is more than twice that of all the other planets combined. When comets pass near it, Jupiter can dramatically alter their paths. Some are accelerated outward, gaining enough energy to leave the solar system entirely. Others are slowed and captured into new orbits. In fact, there are objects in our system today whose unusual, highly tilted or even backward-moving orbits suggest they may have originated elsewhere and been captured long ago. The solar system is not sealed. It is porous, and this porous boundary is what allowed Oumuamua to pass through, not as an anomaly of physics, but as part of a much larger, slower exchange happening quietly across the galaxy. So by the time we detected it in October of 2017, Oumuamua was not just a single object. It was evidence of something larger, that star systems are not isolated. They are participants in a slow, ongoing circulation of matter, a circulation so gentle and vast that we're only just beginning to notice it. And yet, even in that enormous context, Oumuamua did something that made astronomers pause. Not because it was interstellar, but because it did not move quite the way it should have. And that is where our quiet investigation begins to narrow from the scale of the galaxy to the subtle behaviour of one small, tumbling fragment of rock and ice. When we think about the solar system, we often imagine the sun as the central authority, the great anchor holding everything in place, and that is mostly true. The sun contains more than 99% of all the mass in our system. Its gravity governs the long dance of the planets. But there is another body whose influence is surprisingly profound: Jupiter. Jupiter is not merely the largest planet, it is a gravitational architect. Its mass is more than twice that of all the other planets combined. If the solar system were a small town, Jupiter would be the towering mountain just beyond its borders, shaping the winds, redirecting the rivers, and altering the paths of anything that wanders too close. In the outer reaches of the solar system, where comets travel on long, stretched-out orbits, Jupiter acts as both guardian and disruptor. When an icy body drifts inward from the distant Oort cloud, it may pass near Jupiter long before it approaches the inner planets, and when that happens, its future can change dramatically. If Jupiter's gravity pulls in just the right way, it can slow an object down slightly. Not enough to trap it immediately, but enough to reshape its orbit. A comet that once took millions of years to circle the sun might suddenly find itself on a much shorter path. But gravity can also do the opposite. Imagine rolling a small stone past a massive boulder. If the angle is just right, the stone can be flung outward faster than it arrived. In orbital mechanics, this is called a gravitational assist. Space agencies use this technique deliberately, sending spacecraft past planets to gain speed without burning extra fuel. Nature does the same thing. In 1980, a comet known as C/1980E1 passed unusually close to Jupiter. Before that encounter, it was bound to the Sun on an extremely long orbit, taking over 7 million years to complete a single circuit. But Jupiter's gravitational influence accelerated it just enough to push it onto a hyperbolic path. That means it gained sufficient energy to escape the solar system entirely. It became, in effect, an interstellar object in the making. Over the next few million years, it will drift farther and farther from the Sun, eventually joining the population of wandering debris between the stars. Jupiter had quietly cast it out. But there are also hints that Jupiter may have done the opposite in the distant past. Some objects in our solar system travel on unusual orbits, tilted sharply compared to most planets, or even moving in the opposite direction around the Sun. This backward motion is called retrograde orbit. It is rare among large bodies in our system. When astronomers see an asteroid or comet moving in such an unexpected way, they take notice. It may not prove an interstellar origin, but it raises questions. One particularly intriguing object, whose Hawaiian name is long and melodic, moves in a 1-to-1 orbital resonance with Jupiter. That simply means it shares the same orbital period as Jupiter, circling the Sun once in the same amount of time, yet its orbit is tilted and unusual. Some researchers have suggested it could be a captured interstellar asteroid, trapped long ago when the solar system was younger and more chaotic. If that is true, then fragments from other stars may already be here, quietly orbiting the Sun for billions of years, unnoticed until modern telescopes became precise enough to study them carefully. This possibility reframes our perspective. Oumuamua may have been the first confirmed interstellar visitor detected passing through, but it may not have been the first ever to enter. It was simply the first we clearly recognized. The solar system, then, is not a sealed container. It is more like a harbour. Objects arrive, some leave, a few may stay. Jupiter plays a central role in this exchange. Its gravitational reach extends far beyond its visible disk. When a small object approaches, Jupiter's gravity can either tighten its orbit, slow it, or accelerate it outward. The outcome depends on speed, angle, and timing. It is a delicate dance governed by momentum and energy, and this brings us back to an important idea. For an object to escape the Sun permanently, it must be travelling faster than the escape speed at its distance. That speed decreases the farther you are from the Sun. At Earth's distance, the escape speed from the solar system is about 42 kilometers per second. Farther out, it is lower. When Oumuamua entered the solar system, it was already moving faster than the escape speed. That is how astronomers knew it didn't originate here. It was never gravitationally bound to the Sun. It came in on a hyperbolic trajectory, a path shaped like a wide open curve rather than a closed ellipse. As it fell toward the Sun, gravity accelerated it, just as gravity accelerates a comet falling inward. At its closest point, it was moving at about 87 kilometers per second. That is 87,000 meters every second, faster than any spacecraft humanity has launched. Then it began to climb back outward. In a simple, predictable universe, it would have slowed exactly according to gravitational calculations. But careful measurements showed something slightly different. A small additional acceleration appeared to push it away from the Sun more strongly than gravity alone would allow. Not dramatically, not violently, just subtly. Subtle enough that it required precise calculations to detect, but real. At this stage in our story, we have established something quietly profound. The galaxy exchanges fragments between star systems. Jupiter can eject or capture wandering bodies. The solar system is porous. Interstellar debris exists. None of that is mysterious. What made Oumuamua extraordinary was not that it came from elsewhere. It was that once it was here, it behaved in a way that required explanation. The push it experienced was small, far weaker than the pull of Earth's gravity on your body right now. But in the vacuum of space, even a very small force, sustained over time, can change a trajectory. And in physics, objects do not accelerate without cause. Something was pushing it. The question was no longer where it came from. The question had become far more precise. What force, natural or otherwise, could account for that gentle, persistent nudge? And as astronomers began examining the data more closely, the possibilities narrowed to just a few. Some were familiar, some were controversial, and some would ignite one of the most public scientific debates in recent memory. By the time astronomers noticed Oumuamua, it had already completed the most dramatic part of its visit. It had passed its closest point to the Sun on September the 9th, 2017. At that moment, it was moving at roughly 87 kilometers per second, curving tightly around our star before beginning its long departure back into interstellar space. No alarms sounded, no headlines appeared. The object was still unknown. It was not until October 19th that the Pan-STARRS telescope system at Haleakala Observatory in Hawaii detected something unusual. Pan-STARRS is designed to scan the sky repeatedly, searching for objects that move against the steady background of stars. Most of what it finds are near-Earth asteroids or distant comets, objects that belong to our solar system. But this one moved differently. At first, it was catalogued as a comet. That is a reasonable assumption when a small, fast-moving object is discovered. Comets often arrive from the distant Oort cloud on long, elongated orbits. It was given the temporary designation C/2017 U1. However, when astronomers looked more closely, they could not see the fuzzy cloud of gas and dust, called a coma, that usually surrounds a comet as it warms near the sun. Without that visible signature, it was reclassified as an asteroid. Its label changed to A/2017 U1. That alone was unusual. Objects are not often reclassified so quickly. But the real surprise came when its orbit was calculated with greater precision. The shape of an object's path around the sun tells you whether it belongs to the solar system. Most planets and asteroids follow elliptical paths, closed loops that bring them back again and again. But this object's path was not a loop. It was open. Its orbit was hyperbolic, meaning it was shaped like a wide, sweeping curve that would never close back on itself. The object was moving too fast to be captured by the sun's gravity. It was simply passing through. For the first time in human history, we had detected a confirmed interstellar object in real time. The International Astronomical Union, the body responsible for naming and classifying celestial objects, faced an unusual task. There had never been a confirmed object from another star system before, so a new category was created. The letter I was chosen to stand for interstellar. This object became known as 1I/2017 U1, but it was also given a Hawaiian name, Oumuamua. It means scout, or first messenger from afar. The name feels appropriate. It was small, perhaps somewhere between 100 and 1,000 meters in length. Precise measurements were difficult because the object was faint and receding quickly. We never resolved it directly as an image. Instead, we inferred its properties from the way its brightness changed over time. As it rotated, the amount of sunlight it reflected toward Earth fluctuated dramatically. Every 7 hours or so, its brightness rose and fell. That suggested an elongated shape. If you imagine a long, narrow object tumbling through space, it reflects more light when its broader side faces us, and less when its narrow edge turns toward us. Some researchers proposed that it resembled a cigar, long and thin. Others suggested it might be more like a flattened disc, like a pancake turning in slow motion. The data could support either interpretation. What was clear is that it was not spherical. Even more, intriguingly, it did not rotate smoothly around a single stable axis. It appeared to tumble, wobbling as it spun. In physics, this kind of motion is known as non-principal axis rotation. But we can think of it more simply as a spinning object that has not yet settled into a stable rhythm, like a coin that wobbles before lying flat. That tumbling hinted at a past disturbance. Perhaps it had collided with something long ago. Perhaps it had been violently ejected from its original star system. But the time window for study was short. When it was first detected, Oumuamua was already about 33 million kilometers from Earth. That may sound close in cosmic terms, but at that distance, even large telescopes struggle to gather detailed information from a small, dark object. Astronomers around the world mobilized quickly. Observatories pointed their instruments toward the fading visitor. The Spitzer Space Telescope attempted to detect infrared radiation from it, which could reveal heat signatures and possibly the presence of gas. Spitzer observed for 30 hours. It detected nothing. No infrared glow, no clear evidence of gas emission. By mid-December, barely 2 months after its discovery, Oumuamua had become too faint to study effectively. It was already heading outward at roughly 26 kilometers per second, climbing away from the Sun and from us. In cosmic time, it had barely paused. This brief observational window has shaped everything that followed. We are trying to understand an object we observed only in passing, with limited data, under time pressure. And yet, from that limited data, one detail stood out. As astronomers tracked its motion with increasing precision, they noticed that its trajectory did not align perfectly with predictions based on gravity alone. When an object swings around the Sun, its path can be calculated with remarkable accuracy using Newton's law of gravitation and Einstein's refinements for relativity. The mathematics are well tested. We use them to guide spacecraft across billions of kilometers, but Oumuamua deviated slightly. The deviation was not dramatic. It was subtle, like a small correction in its outward path. Over weeks of observation, the object appeared to accelerate away from the Sun just a little more strongly than expected. The measured acceleration was extremely small, on the order of a few millionths of a meter per second, applied continuously. That is far weaker than the acceleration you feel standing on Earth. But in the emptiness of space, even a tiny sustained push can alter a trajectory measurably. In physics, acceleration does not happen without cause. If gravity alone could not account for the motion, then some additional force must have been acting on the object. The simplest explanation would be outgassing. Gas escaping from the surface like a gentle thruster, pushing it away from the Sun. But no visible gas or dust had been detected. This was the moment the mystery truly began. Not because the object came from another star, but because something, however small, was pushing it. And as scientists examined that subtle push, they found themselves considering explanations that range from the familiar to the extraordinary. We never saw Oumuamua directly. No spacecraft flew past it. No telescope captured a detailed image showing craters or ridges. Everything we know about its shape comes from something much simpler and much more delicate. Light. When sunlight strikes an object in space, a portion of that light reflects back toward us. As the object rotates, the amount of reflected light changes depending on which side is facing Earth. By carefully measuring those changes in brightness over time, astronomers can reconstruct a surprising amount of information. This method is called light curve analysis, but we can think of it more intuitively. Imagine holding a spoon under a lamp and slowly rotating it. Sometimes the curved surface catches the light and flashes brightly. Other times, when the thin edge faces the lamp, it reflects much less. Even without seeing the spoon clearly, you could infer its shape just by watching how the brightness changes. That is exactly what astronomers did with Oumuamua. They noticed that its brightness varied dramatically, by a factor of nearly 10, over a rotation period of about 7 hours. That is a very large variation. Most asteroids in our solar system show only modest changes in brightness as they rotate, because they are not extremely elongated. For Oumuamua, the change was extreme. This suggested that it was either very long and thin, like a cigar tumbling through space, or perhaps very flat and broad, like a pancake turning edge-on and face-on in alternating views. Both shapes could produce similar brightness variations, depending on the angle from which we observed it. Early interpretations lean toward the elongated model, a body, several times longer than it was wide, but later analyses suggested that a flattened disc-like shape might actually better fit the data. What remains clear is that it was not spherical. It was not even roughly round. It was something more extreme. Adding to the puzzle, the rotation itself was not simple. Many asteroids rotate steadily around a stable axis like a spinning top, but Oumuamua appeared to tumble. Its rotation was complex, shifting slightly over time, not perfectly periodic. In physics, this kind of motion is sometimes called non-principal axis rotation, but we can imagine it more gently as a spinning object that has not quite found its balance. Like a book tossed into the air, flipping unpredictably rather than rotating smoothly. Such tumbling can occur after a collision. If an object is struck hard enough, it can be knocked into an irregular spin state that may persist for millions of years, especially in the frictionless environment of space. This detail suggests a past event, perhaps a violent ejection from its original system. But there was another surprising aspect of its surface. When the Spitzer Space Telescope attempted to detect infrared radiation from Oumuamua, it found none. Infrared observations are sensitive to heat. Even a small object warmed by sunlight should emit some faint glow in the infrared part of the spectrum. Spitzer observed for roughly 30 hours and still detected nothing. This non-detection placed important limits on its size and reflectivity. If an object is dark and absorbs most of the sunlight that hits it, it warms up and emits infrared radiation. If it reflects more light, it stays cooler and emits less infrared radiation. Since Spitzer did not see a heat signature, one interpretation was that Oumuamua might be smaller than initially thought, but relatively reflective. Some analyses suggested it could be at least 10 times shinier than a typical comet. That does not necessarily mean it was metallic, as some headlines suggested. Reflectivity depends on many factors, including surface texture and composition. But it did hint that its surface might have been unusual compared to the dusty, dark comets we often observe. And then there was its colour. Observation showed that Oumuamua had a slightly reddish hue. Not bright red, but subtly tinted. This is consistent with many objects in the outer solar system whose surfaces have been exposed to cosmic radiation for long periods. Over millions of years, radiation can chemically alter surface materials, creating complex organic compounds that give a reddish tint. If Oumuamua wandered through interstellar space for billions of years, its surface may have been slowly weathered by high-energy particles. It may have developed a thin crust, hardened and darkened over time. That crust could help explain something important. If the object contained volatile materials, such as water ice, deep inside, a hardened outer layer might prevent obvious outgassing when warmed by the sun. Instead of dramatic jets of gas and dust forming a bright coma, the object might release material more subtly, or perhaps not visibly at all. This idea would become central in later explanations of its mysterious acceleration. But at this stage in our story, astronomers were still assembling clues. They had an object that was small, perhaps a few hundred meters across, extremely elongated or unusually flat, tumbling rather than rotating smoothly, more reflective than many known comets, and travelling on a hyperbolic trajectory from outside the solar system. All of this was fascinating. None of it by itself required extraordinary explanations. The universe is full of strange shapes. Collisions can produce shards and fragments. Radiation can sculpt surfaces in ways that seem exotic from afar. But then came the detail that would transform curiosity into debate. As Oumuamua moved away from the sun, careful tracking revealed that it was not slowing down exactly as predicted by gravity alone. The deviation was small but persistent. If we imagine its motion as a line drawn across a chart, the actual path drifted slightly away from the purely gravitational curve. The difference accumulated gradually over weeks. It was as if something invisible were giving it a faint push, always directed away from the sun. In space, such a push can arise from gas escaping from a surface. When gas flows outward, it produces a reaction force in the opposite direction, like a tiny thruster. This is common for comets. As ice warms and turns directly into vapour, a process called sublimation, the escaping gas pushes the comet gently. But for Oumuamua, no visible gas or dust had been detected. No bright tail, no cloud, no clear sign of activity. This left astronomers with a delicate problem. They had to explain a force that appeared to exist without clear evidence of the usual cause. And in science, when the simplest explanation seems absent, the imagination begins to widen, not wildly, but cautiously. Because if there was no visible outgassing, then what exactly was pushing this ancient, tumbling shard of matter away from our sun? Up to this point, everything about Oumuamua, while unusual, could still fit within the wide diversity of natural cosmic objects. Strange shape, tumbling rotation, reddish surface, hyperbolic path. All of these could be explained as the consequences of collisions, radiation, and long journeys through space. But then came the detail that refused to settle quietly into place. As astronomers continued to track Oumuamua's motion, they noticed that its outward journey from the Sun did not follow the precise curve predicted by gravity alone. In celestial mechanics, the motion of objects under gravity is extraordinarily predictable. We can send spacecraft across billions of kilometers and guide them to distant planets using calculations based on gravity. The mathematics are not guesses. They're tested, refined, and trusted. So when Oumuamua's trajectory showed a small but measurable deviation, it drew attention. The acceleration was tiny, on the order of a few millionths of a meter per second, applied continuously over time. That may sound negligible, and on Earth it would be. But in the vacuum of space, where friction is essentially absent, even a small force sustained for weeks can shift an object's path in a detectable way. It was as if a faint, steady breeze were pushing on it. Importantly, the direction of this acceleration was away from the Sun. That detail mattered. If something were pushing it randomly, the direction might change. But this push seemed aligned with the Sun object line, as though some process connected to sunlight was responsible. The first and most natural explanation was outgassing. When comets approach the Sun, heat causes ice within them to sublimate, that is, to turn directly from solid into gas. The escaping gas flows outward, forming a glowing coma and often a tail. At the same time, this gas acts like a miniature rocket engine. As material shoots out one side, the comet experiences a reaction force in the opposite direction. This process can cause a comet to accelerate slightly away from the Sun. It is well understood. It has been measured many times. So the simplest hypothesis was that Oumuamua was behaving like a comet. But there was a problem. Despite careful observation, no coma was detected. No visible cloud of dust. No bright tail. The Spitzer Space Telescope, which is sensitive to infrared radiation and can detect heat signatures from gas and dust, observed for roughly 30 hours and still found nothing. No clear emission from carbon dioxide, no sign of carbon monoxide, none of the typical gases we associate with active comets. It was as though the expected exhaust plume simply was not there. Some researchers suggested that perhaps the outgassing was too weak to produce a visible coma, yet strong enough to cause the observed acceleration. Others proposed that if the object had developed a hardened outer crust during its long interstellar journey, the escaping gas might be minimal or released in a more diffuse way. But another subtle issue emerged. If gas were escaping unevenly from the surface, it would not only push the object, it would also apply torque. Torque is a twisting force. When gas escapes from one side, it should cause the object to spin differently, perhaps even dramatically. And yet, while Oumuamua was tumbling, its rotation did not show the kind of rapid changes that strong, uneven outgassing would typically cause. This became known informally as the torque problem. The acceleration and the rotation had to be consistent with the same physical process. It was not enough to explain one without the other. The puzzle grew slightly deeper. If typical cometary gases were not detected, perhaps the escaping material was something harder to observe. Hydrogen gas, for example, is very difficult to detect directly in space. It does not emit strong visible signatures the way carbon-based gases do. One early idea suggested that Oumuamua might be composed largely of frozen molecular hydrogen. As it warmed near the sun, that hydrogen could sublimate and escape invisibly, producing the gentle acceleration without leaving a detectable dust trail. But there was a difficulty with that idea. Molecular hydrogen ice is fragile. In the radiation-filled environment of interstellar space, pure hydrogen ice would likely erode or disperse over long timescales. Calculations indicated that a hydrogen iceberg wandering for millions of years might not survive the journey intact. The hypothesis faded, but the broader idea that invisible gas might be responsible remained alive. Another possibility involved the pressure of sunlight itself. Light carries momentum. When photons strike an object, they transfer a tiny amount of force. This is known as radiation pressure. It is extraordinarily weak but measurable. Spacecraft have even been designed with large reflective sails that use sunlight as propulsion. If Oumuamua were extremely thin and broad, almost like a sheet, then radiation pressure might produce the observed acceleration. For that to work naturally, however, the object would need to be exceptionally thin, perhaps less than a millimeter thick if it were hundreds of meters wide. That geometry would be difficult to produce through natural processes, though not impossible. This proposal attracted significant attention because of its implications. If such an object were artificial, a late sail from another civilization, it could explain both its shape and its acceleration. But extraordinary claims require extraordinary evidence, and so most astronomers continued searching for explanations grounded in familiar physics. The key was this: whatever was pushing, Oumuamua had to produce a steady, sunward-aligned acceleration of a few millionths of a meter per second, without generating visible dust or dramatic torque effects. A subtle push, sustained, invisible. As data were analysed and reanalyzed, one emerging idea began to gain traction. It involved not exotic hydrogen icebergs, nor alien technology, but something more familiar: water ice. Laboratory experiments have shown that when water ice is exposed to high-energy radiation, similar to cosmic radiation in interstellar space, it can undergo chemical changes. The radiation can break apart water molecules and produce molecular hydrogen within the ice. That hydrogen can become trapped in microscopic pockets. Later, when the ice warms, its structure rearranges. The trapped hydrogen can be released gradually, without explosive jets or visible dust. In other words, an object made largely of water ice that has spent millions of years exposed to radiation might carry hidden stores of hydrogen gas within it. As it passed near the sun, gentle warming could cause that hydrogen to seep out, producing a faint but steady push, invisible, subtle, but sufficient. This idea would eventually be formalized into what some researchers began calling the dark comet hypothesis, a category of objects that accelerate due to gas release, but without bright comas or visible tails. At this stage, the mystery was no longer whether a force existed. It was clear that it did. The question was whether that force required new physics, or simply a deeper understanding of how familiar materials behave after eons in interstellar space. And the answer, as often happens in science, was not dramatic. It was patient. But before we settle too comfortably into that explanation, we must look beyond Oumuamua itself. Because if this mechanism is real, then it should not be unique. There should be others. And quietly, within our own solar system, astronomers began to notice that perhaps there were. When astronomers first noticed that faint, steady acceleration, just a few millionths of a meter per second sustained over weeks, the most natural thought was not extraordinary at all. Perhaps Oumuamua was simply a comet. Comets are known to accelerate when they approach the sun. As sunlight warms their surface, ice turns directly into gas in a process called sublimation. The gas escapes into space, and by Newton's quiet and reliable principle, for every action there is an equal and opposite reaction. The comet experiences a small push in the opposite direction. It is like a snowball warming in sunlight. As it melts, you might expect to see droplets of water forming and dripping away. In space, instead of droplets, you get vapour. And when that vapour streams outward, it acts like a gentle thruster. This is not speculative. We have measured it many times. Traditional comets develop glowing comas, hazy envelopes of gas and dust, and often long, luminous tails shaped by sunlight and the solar wind. The escaping material not only makes them beautiful, but also subtly changes their motion. So when Oumuamua accelerated away from the sun more strongly than gravity alone predicted, sublimation was the obvious candidate, but something did not match. Despite intense observation from telescopes around the world, no visible coma appeared. There was no glowing cloud, no bright plume of dust, no tail stretching behind it. The object remained sharp and star-like, even under careful imaging. Astronomers then turned to infrared observations. If gas and dust were escaping, even if too faint to see in visible light, the object should still emit heat. As material sublimates, it carries energy, and a warming body radiates infrared light. The Spitzer Space Telescope observed Oumuamua for roughly 30 hours. It searched for signs of carbon dioxide and carbon monoxide, two gases commonly released by comets. It looked for the faint thermal glow that dust and gas would produce. It detected nothing. This non-detection was not dramatic. There was no flashing warning, but it placed important limits on what could be happening. If typical cometary gases were escaping in quantities large enough to produce the observed acceleration, then Spitzer should have seen something. Even a weak coma usually leaves a detectable signature. And yet the data remained quiet. This created a delicate tension. On one hand, the acceleration looked comet-like. On the other, the absence of visible gas made it unlike any comet we had previously observed. Could it be that the outgassing was simply too weak to form a visible cloud? After all, Oumuamua was small, perhaps only a few hundred meters across. A modest release of gas might provide enough thrust to account for the acceleration without creating a dramatic tail. That possibility could not be dismissed immediately. But when researchers calculated how much material would need to escape to produce the measured push, they encountered another subtle issue. Even a small but continuous release of gas should have produced some observable signature, either in brightness, in spectral lines, or in thermal emission. The silence was persistent. It was as though a snowball were warming in sunlight, but leaving no visible steam. That image captures the puzzle. If ice was sublimating normally, we would expect to see evidence, yet none appeared. One way to reconcile this would be to imagine that the ice was buried beneath a hardened crust. Over millions of years in interstellar space, cosmic radiation can alter the outer layers of icy bodies. It can darken and compact the surface, creating a protective shell. If volatile materials were trapped beneath such a crust, they might escape more gradually, or through microscopic pores rather than dramatic jets. This could reduce the visibility of the outgassing. But even then, the numbers had to align. The observed acceleration was small but precise. It required a sustained force directed away from the Sun. If sublimation were responsible, the rate of gas loss would have to be carefully balanced. Not too much, not too little. Too strong, and a coma should have been obvious. Too weak, and the acceleration would not match. This narrow range of possibilities made astronomers cautious. They were not rejecting the comet hypothesis outright. Rather, they were refining it, asking whether it could operate in an unfamiliar way, quieter, subtler, almost hidden. It is important to remember how brief the observational window was. Oumuamua was already departing when discovered. By the time detailed studies began, it was tens of millions of kilometers away, fading steadily. Perhaps the activity had peaked earlier before we noticed it. Perhaps the orientation of the object concealed any escaping gas from our vantage point. Perhaps the dust particles were unusually large or unusually small, altering how they scattered light. Each possibility was examined carefully. But the central question lingered. Can an object behave like a comet, accelerating due to sublimation, while showing no visible signs of being one? If the answer were yes, then Oumuamua would not require exotic explanations. It would simply represent an extreme case within the natural diversity of icy bodies. If the answer were no, then something deeper was at work. At this stage in the investigation, the mystery was not about aliens or artificial structures. It was about whether familiar physics, ice, sunlight, and gas, could account for what we observed. The idea of a comet in disguise is not dramatic. It is patient. It asks us to consider that the universe may be subtler than our categories suggest. Not every comet must look like a glowing snowball with a streaming tail. Some might be quiet. Some might warm without spectacle. Some might leave only the faintest trace of their activity, a gentle nudge detectable only through careful calculation. But if gas were, indeed, escaping, there would be another consequence. Gas does not only push, it twists. And that leads us to the next layer of the puzzle, one that involves not just motion through space, but motion around itself. If gas were escaping from Oumuamua, quietly, invisibly, gently, then physics tells us something else should have happened as well. Gas does not only push an object forward, it twists it. When a comet releases material, the escaping gas rarely flows perfectly evenly from every direction at once. Instead, it tends to escape from specific regions where sunlight warms the surface more strongly, perhaps from cracks, vents, or patches of exposed ice. These localized jets act like tiny thrusters attached to different parts of the object, and whenever a force is applied off-center, it creates torque. Torque is simply a twisting force. If you push on the edge of a door rather than at its hinge, the door swings open. The farther from the hinge you push, the stronger the twist. The same principle applies in space. If Oumuamua were losing gas from one side more than another, the escaping material should not only accelerate it away from the Sun, but also alter its rotation. It might spin faster, it might change its axis of rotation, it might even enter a chaotic tumble. At first glance, this might not seem problematic, because Oumuamua was already tumbling. Its brightness variations showed that it was not rotating smoothly around a single stable axis. Instead, it appeared to wobble in a complex way, as though spinning unevenly through space. But here is the subtle issue. The tumbling motion that astronomers observed did not appear to be rapidly changing during the period of measured acceleration. The rotation state was complicated, yes, but it was not evolving violently. If strong jets of gas were responsible for the acceleration, they should also have produced noticeable changes in the rotation rate over the weeks of observation. Yet those changes were not seen at the level one might expect. This tension became known informally as the torque problem. It is not dramatic, It is not explosive. It is simply a mismatch between two behaviours that should be linked. If sublimation were pushing the object away from the Sun, then the same process should have been twisting it significantly. But the observed spin did not show the kind of rapid evolution typical of active comets, experiencing strong, uneven outgassing. To make the comet hypothesis work, the gas release would need to be remarkably uniform, distributed across the surface in such a way that it provided net acceleration without substantial torque. That is possible in theory. If the object were shaped in a certain way, or if the gas seeped out evenly across broad regions rather than erupting in concentrated jets, then the torque might be minimal. But that requires fine balance. Imagine holding a balloon filled with air. If the balloon has a small hole on one side, air escapes in a narrow stream. The balloon jerks and spins unpredictably as it empties. But if instead the balloon were made of a porous material, releasing air gently and evenly from its entire surface, the motion would be smoother. The balloon might drift rather than spin wildly. The torque problem asks which of these scenarios better fits Oumuamua. If the acceleration were caused by narrow jets, we would expect dramatic changes in rotation. If it were caused by diffuse release, the torque might be small enough to escape detection. The observational data showed a tumbling object. Yes, but not one rapidly spinning up or reorienting during the period of measured acceleration. And this is where the puzzle deepened. The magnitude of the acceleration was small, only a few millionths of a meter per second applied steadily. But even small forces, when applied asymmetrically over time, can change rotation noticeably. The question became quantitative. How much gas would need to escape to produce the observed push? Where would it have to escape from? And how would that affect the spin? Researchers modelled various scenarios. They simulated different shapes, different distributions of ice, different patterns of sunlight exposure. Some configurations could reproduce the acceleration while keeping torque modest. Others led to spin rates that did not match observations. The difficulty was not insurmountable, but it required careful tuning. And this is often the point in science where multiple explanations compete. If a model requires too many special conditions, too many precise alignments, it begins to feel less natural. The comet hypothesis was still viable, but it was becoming increasingly delicate. The torque problem did not eliminate sublimation as a cause. It simply narrowed the range of acceptable scenarios. The gas would have to escape gently, perhaps through microscopic channels. The thrust would have to be nearly symmetric. The distribution of material would have to be just right. None of these are impossible, but they are specific. Meanwhile, the acceleration remained real, measured, consistent across independent observations. The object was being pushed, and yet the expected signs of strong uneven gas jets were absent. It was like a leaking balloon that should wobble wildly, but instead drifts almost serenely. It spins steady and complex, but not violently changing. This subtle mismatch kept the debate alive, because in physics, forces and motion are intimately connected. If one is observed without the full consequences of the other, we look closer. The torque problem does not shout, it whispers. It asks whether the comet explanation can truly account for all observed behaviour, not just the acceleration, but the rotation as well. And if that explanation becomes too finely tuned, then alternative ideas begin to feel more attractive. Not because they are dramatic, but because they may offer a cleaner fit. And so, as the comet in disguise scenario strained gently under the weight of torque considerations, attention began to shift toward another possibility, one that involved not escaping gas, but the pressure of light itself. By now, the comet explanation had been stretched carefully across the data. Ice turning into gas, subtle sublimation, perhaps hidden beneath a crust, perhaps too faint to see, perhaps oriented in a way that concealed its activity from Earth. It was a reasonable path, but science does not move forward by protecting a single idea. It moves by testing alternatives. And so, some researchers asked a different question. If gas is not clearly visible, what else could provide a steady push away from the sun? The answer begins with something almost poetic. Light has weightless touch, but not weightless influence. Sunlight carries momentum. When photons strike a surface, they transfer a tiny amount of force. On Earth, this force is so small that we never notice it. But in space, where there is no air resistance and almost no opposing drag, even a very small continuous force can matter. This phenomenon is called radiation pressure. It is not speculative. Engineers have designed spacecraft that intentionally use it. A solar sail is a large, ultra-thin reflective sheet that captures the momentum of sunlight. The push is gentle, almost imperceptible at any single moment. But over time, it can steadily accelerate a craft without using fuel. Imagine placing a wide sheet in a steady breeze. The wind is not violent, it does not shove abruptly, but it continues, minute after minute, and gradually the sheet moves. In the vacuum of space, sunlight can be that breeze. When researchers calculated the acceleration of Oumuamua, again, only a few millionths of a meter per second, applied continuously, they noticed that the magnitude was in the same general range that radiation pressure could produce if the object had the right geometry, and that if is crucial. For sunlight alone to account for the observed acceleration, the object would need a very large surface area compared to its mass. In other words, it would need to be extremely thin and relatively broad. If Oumuamua were hundreds of meters across but only a fraction of a millimeter thick, then radiation pressure could provide enough force to explain its motion. That is an unusual structure. Natural asteroids and comet fragments tend to be roughly comparable in all dimensions. Collisions break rock into irregular chunks. Even flattened shards are usually thick relative to their length. A sheet thinner than a coin, spanning hundreds of meters, would be difficult to produce through known natural processes. This line of reasoning was developed most prominently by astrophysicist Avi Loeb. He suggested that if the object were extremely thin and reflective, radiation pressure could explain both the magnitude and direction of the acceleration, and, if such a structure were unlikely to form naturally, one might consider another possibility: a light sail. Not necessarily an active spacecraft, not necessarily functioning, perhaps debris, perhaps abandoned technology, perhaps something we do not yet understand. The idea travelled quickly through media headlines, but within the scientific community the tone remained cautious. The physics of radiation pressure is real. The question was not whether light can push. It can. The question was whether the required geometry was plausible. There were immediate challenges. First, durability. If an object only a fraction of a millimeter thick had wandered through interstellar space for millions of years, it would have endured countless impacts with microscopic dust grains. Even tiny collisions at high speed can gradually erode material. Cosmic radiation would also degrade thin structures over long timescales. Could such a delicate sheet survive intact? Second, rotation. Oumuamua was tumbling, not rotating smoothly like a stabilized sail. A functional solar sail, whether natural or artificial, would typically maintain a stable orientation relative to the sun to maximize thrust. But Oumuamua's rotation was complex and irregular. Third, composition. No metallic reflection was detected. Its colour was slightly reddish, consistent with radiation-weathered organic compounds, rather than highly reflective engineered material. None of these points definitively rule out the radiation pressure explanation, but they shift the burden of probability. In science, we often apply a principle of parsimony. The explanation that introduces the fewest new assumptions is generally preferred, provided it accounts for the data. If radiation-altered ice can explain the acceleration without invoking exotic geometry, then the natural explanation remains stronger. Yet it would be a mistake to dismiss the sail hypothesis entirely. It served an important purpose. It forced researchers to calculate carefully, to re-examine the acceleration magnitude, to model how thin an object would need to be, to consider how radiation pressure scales with distance from the sun. It reminded the community that even gentle forces, sunlight for instance, can accumulate into measurable effects, and it expanded the public imagination. There is something deeply human about looking at a mysterious object from another star and wondering whether it might carry intention. But science is patient. It does not reject ideas because they are bold, nor does it accept them because they are exciting. It weighs them. In the case of Oumuamua, most astronomers concluded that while radiation pressure could theoretically account for the acceleration under very specific conditions, the required thinness and structural integrity made a natural ice-based explanation more likely. Still, the sail hypothesis remains part of the conversation, not because it is widely accepted, but because it reminds us how little data we truly had. We never saw the object up close. We never measured its thickness directly. We inferred its shape from reflected light and its motion from careful tracking. When evidence is limited, uncertainty remains, and that uncertainty is not a flaw. It is simply the quiet space where understanding is still forming. Whether Oumuamua was a shard of ice slowly releasing trapped gas, or a naturally flattened fragment unusually sensitive to sunlight, or something even more subtle, it did something important. It expanded the range of what we consider possible. It made us think more carefully about forces we normally ignore, and it prepared us for the next visitor, who may arrive sooner than we expect. Because if one object can surprise us, another almost certainly will. After the sail hypothesis widened the imagination, after sunlight itself had been considered as a possible engine, the conversation slowly returned to something quieter. What if the answer was not exotic at all? What if the key lay not in advanced civilizations or ultra-thin structures, but in something as ordinary as water ice? Water ice is not as simple as it appears. In the laboratory, when scientists expose ice to high-energy radiation, similar to the cosmic rays that permeate interstellar space, they observe subtle chemical changes. The radiation can break apart water molecules, which are made of 2 hydrogen atoms and 1 oxygen atom. When these bonds are disrupted, molecular hydrogen, made of 2 hydrogen atoms, can form inside the ice. Over time, tiny pockets of hydrogen gas can become trapped within the frozen structure. Imagine an ancient block of ice, drifting between the stars for millions of years. Invisible radiation passes through it. Bonds break and reform. Microscopic bubbles accumulate, too small to see, too quiet to notice. The surface of the ice slowly hardens. Radiation compacts and alters the outer layers, forming a crust. Beneath that crust, hydrogen gas remains locked within crystalline cavities. This is not speculation alone. Laboratory experiments have demonstrated that irradiated ice can store molecular hydrogen in this way. The process is subtle, but real. Now imagine that this ancient fragment enters a new star system. It begins to warm, not dramatically at first, just gently, as it approaches closer to the star. The temperature rises, the ice structure begins to rearrange at a microscopic level. Those trapped hydrogen molecules, once confined, start to migrate. They find pathways outward through pores and fractures, and slowly the ice exhales, not in jets, not in bright plumes, but in a diffuse release of light, invisible gas. Hydrogen is difficult to detect under these conditions. It does not carry dust with it the way typical cometary activity does. It does not form a glowing coma easily observable in visible light. And in small quantities, it may not produce a strong infrared signature either, yet even a gentle continuous release can produce thrust. The acceleration observed for Oumuamua was small, only a few millionths of a meter per second sustained over time. A slow seep of hydrogen, distributed relatively evenly across the surface, could provide such a push without generating dramatic torque. This is where the torque problem and the comet disguise idea begin to converge. If the gas release were diffuse, more like a slow permeation than concentrated jets, the twisting force would be minimized. The object might continue tumbling in its existing complex rotation, but without rapidly changing its spin rate. The hydrogen would act less like a rocket engine and more like a quiet breath. This model was explored in detail by researchers Darryl Seligman and Jennifer Bergner. They proposed that Oumuamua might represent a new category of object, one shaped by radiation chemistry during a long interstellar journey. Not a traditional comet, not a rocky asteroid, but something in between, a dark comet. The word dark here does not mean mysterious or ominous. It simply reflects the absence of visible brightness features. A comet that accelerates but does not glow. This idea elegantly addresses several constraints at once. It explains why the acceleration was directed away from the sun, because warming drives gas release. It explains why no visible dust was detected, because hydrogen does not easily carry dust grains outward in the same way heavier gases can. It explains why infrared observations found little, because hydrogen in small quantities radiates weakly, and it explains why the rotation did not change violently, because the release could be relatively uniform across the surface. Of course, like all scientific models, this one must withstand scrutiny. How much hydrogen could realistically accumulate in interstellar ice over millions of years? Would the release rate match the measured acceleration precisely? Would the object's size and shape allow such behavior? Researchers have modeled these questions carefully. Under reasonable assumptions about ice composition and radiation exposure, the numbers align plausibly. Not perfectly, but within the uncertainties inherent in limited observational data. There is something deeply satisfying about this explanation. It does not require unknown materials. It does not require artificial construction. It does not require new physics. It simply extends our understanding of familiar substances, water, hydrogen, radiation, into the context of deep time and interstellar travel. It suggests that small, icy bodies may undergo chemical evolution while drifting between stars, that the galaxy itself slowly sculpts them, not only through collisions but through invisible particle flux. And when they finally encounter warmth again, they respond, not with spectacle, but with subtle motion, like frozen bubbles trapped inside ancient ice, like a glacier slowly releasing air as it melts under sunlight. The image is quiet, and perhaps that quietness is part of why the hydrogen model has gained traction within the scientific community. It preserves parsimony, the preference for explanations that introduce the fewest new assumptions. Yet even as this model strengthens, it leaves room for humility. We did not measure hydrogen directly. We inferred its presence from motion. We observed acceleration and sought a mechanism consistent with the absence of visible gas. That is science at its most careful, assembling indirect evidence, testing alternatives, refining possibilities. If the hydrogen model is correct, then Oumuamua was not a technological artifact, nor an anomaly of unknown origin. It was an ancient shard of ice, altered quietly by radiation, carrying within it microscopic stores of gas accumulated over millions of years. When warmed by our sun, it exhaled, and that exhalation nudged it ever so slightly as it departed, a whisper of motion detectable across tens of millions of kilometers. But there is an important implication. If this mechanism is real, then Oumuamua should not be unique. Other small bodies, perhaps even within our own solar system, might exhibit similar subtle accelerations. And as astronomers looked closer, they began to notice that perhaps they already had. By the time the hydrogen in ice model had been proposed, the mystery of Oumuamua no longer felt like a single, isolated event. It had become a test case. If radiation-altered ice could trap hydrogen and later release it invisibly, then perhaps similar behaviour might be found closer to home. Not in interstellar visitors, but in small bodies already orbiting our sun. So astronomers began looking carefully at the motions of near-Earth objects, asteroids that pass relatively close to our planet and whose orbits are tracked with great precision. Most of these objects follow predictable paths shaped by gravity alone. Occasionally, small deviations occur due to a known effect called the Yarkovsky effect. In simple terms, this happens when an asteroid absorbs sunlight during the day and re-emits that energy as heat later, often during its night. That delayed emission creates a tiny thrust. Over many years, this can slowly alter the asteroid's orbit. The Yarkovsky effect is subtle, but well understood. It depends on rotation, surface properties, and how heat flows through the object. However, when researchers analysed high-precision tracking data, they identified something unexpected. 6 small near-Earth objects were found to exhibit non-gravitational accelerations that could not be fully explained by the Yarkovsky effect alone. These accelerations were tiny, comparable in scale to what had been observed for Oumuamua, only a few millionths of a meter per second, sustained gently over time, not dramatic changes, not abrupt shifts, just a faint persistent push. And like Oumuamua, these objects showed no visible signs of outgassing, no comas, no dust tails, no glowing envelopes of vapour. They appeared inert. Some of these bodies were extremely small, only a few meters across. Others were larger, perhaps tens of meters wide. But all were modest in size compared to typical comets. If hydrogen released from radiation-altered ice were a valid mechanism, then these objects might represent local examples of the same phenomenon. Instead of a singular interstellar mystery, we might be looking at a subtle population of dark comets within our own solar system. The phrase dark comet again does not imply something ominous. It simply refers to an object that behaves dynamically like a comet, accelerating slightly due to gas release, while lacking the bright visual features that normally define cometary activity. Imagine stones drifting through space that are not entirely stone. Imagine that within them, hidden beneath a crust shaped by radiation, are microscopic reservoirs of gas. When warmed, they exhale, not in spectacle, but in silence. The idea shifts the narrative gently. Rather than asking, why was Oumuamua so strange? We begin to ask, have we simply overlooked a quieter class of objects? The solar system is vast. Our surveys have improved dramatically over the past few decades, but we're still discovering small bodies all the time. Many are faint, irregular, and difficult to characterize fully. It is possible that some of them have always exhibited tiny non-gravitational accelerations, but until recently our measurements were not precise enough to detect such subtle effects. Now they are, and the pattern, though small, is suggestive. 6 objects is not a large number. It does not prove a new category beyond doubt, but it does hint that Oumuamua's behaviour may not be unique. There is something deeply calming about this possibility, A mystery that initially seems singular begins to dissolve into a pattern. What once felt extraordinary begins to look like part of a broader spectrum. In science, that shift from anomaly to pattern is powerful. It reduces the need for exotic explanations. It suggests continuity. It reminds us that nature often operates quietly beneath the threshold of spectacle. Of course, caution remains essential. The accelerations measured in these near-Earth objects are extremely small. Determining their precise cause requires careful modelling. Thermal effects, shape irregularities, and measurement uncertainties must all be considered. But if even a fraction of these objects are indeed releasing hydrogen or other gases invisibly, then the dark comet model gains strength. And with strength comes prediction. If this mechanism is real, then we should be able to observe it directly in at least one case. We should be able to approach such an object with instruments capable of measuring its composition, detecting faint gas emissions, and analysing its surface properties up close. Instead of inferring from afar, we could test the idea directly. Fortunately, such an opportunity already exists. Among the 6 quiet accelerators is a particularly intriguing target, an object with a precise designation that reads like a code, 1998 KY26. It is small, it spins rapidly. And within the coming decade, a spacecraft will pass close enough to study it in detail. If hydrogen release is confirmed, if subtle gas emissions are detected without dramatic dust plumes, then the dark comet hypothesis would move from plausible to strongly supported. If no such mechanism is found, then we return to the drawing board. Either way, the story becomes richer. Because what began as a fleeting interstellar visitor has led us to examine our own cosmic neighbourhood more carefully. It has sharpened our instruments, refined our models, and reminded us that sometimes the most important discoveries are not loud. They are small shifts in trajectory, tiny accelerations, measured patiently, understood gradually. The universe may not shout its secrets, it may simply nudge us ever so slightly until we learn to notice. Among the 6 quiet accelerators, one object stands out, not because it is large or bright or dramatic, but because we are going to see it up close. Its designation is 1998 KY26. The name sounds technical, almost cryptic. But behind that sequence of letters and numbers is a very small world. It is only a few tens of meters across, closer in size to a modest building than to a mountain. Compared to most asteroids, it is tiny, and yet it holds enormous importance. 1998 KY26 spins extraordinarily fast. It completes one full rotation in about 10 minutes. That means if you were standing on its surface, if such a thing were possible, you would see the stars sweep across the sky at astonishing speed. A 10-minute day. Such rapid rotation suggests that the object is likely a single solid body rather than a loose pile of rubble. If it were merely a collection of rocks held together weakly by gravity, spinning that quickly might cause it to fly apart. So we imagine a small, compact stone, dark, rapidly turning, drifting quietly through space. It also exhibits a tiny non-gravitational acceleration, similar in scale to what was observed for Oumuamua. Not dramatic, not chaotic, just a subtle deviation from purely gravitational motion. No visible coma has been detected, no bright tail, no obvious outgassing. And this is where the opportunity arises. The Japanese spacecraft Hayabusa 2, which previously visited the asteroid Ryugu and returned samples to Earth, is continuing its journey. In the early 2030s, it is scheduled to fly by 1998 KY26. This will not be a distant telescope observation. It will be an encounter at relatively close range. Instruments aboard the spacecraft will measure the object's composition, analyse its surface properties, and observe it from angles impossible from Earth. For the first time, we'll have a chance to test the dark comet hypothesis directly on a small object exhibiting similar behaviour. If radiation-altered ice lies beneath its surface, subtle signatures may be detectable. Spectrometers could identify water-related minerals. Sensitive instruments might detect faint gas emissions. Even the texture and reflectivity of the surface could reveal clues about its history. And if molecular hydrogen, made of 2 hydrogen atoms, has indeed been accumulating within irradiated ice over long periods, then careful measurement might reveal traces of its release. This would not be a spectacular eruption. It would not produce dramatic plumes. It would be more like a gentle seep, detectable only by instruments designed for precision. The beauty of this mission lies not in drama, but in confirmation. For years, scientists have debated whether the hydrogen release mechanism could explain Oumuamua's acceleration. With 1998 KY26, we may finally observe a similar object closely enough to see whether such processes truly occur. Imagine a small spinning stone, turning every 10 minutes, carrying within it a chemical history written by radiation. Imagine that we approach it, not to claim it, not to mine it, but simply to listen, to measure, to observe. There is something deeply human about that. The spacecraft will not land. It will pass by. But during that passage, cameras and instruments will gather data far richer than anything we could obtain from Earth-based telescopes. If hydrogen release is confirmed, then the dark comet model strengthens considerably. Oumuamua would no longer feel like a lonely anomaly. It would become part of a family, small bodies shaped by radiation and capable of subtle, invisible activity. If no such mechanism is found, if 1998 KY26 behaves purely as a dry, inert rock, then the mystery deepens again. Either outcome is valuable, because science does not seek to defend a hypothesis, it seeks to test it. The scheduled encounter also reminds us how quickly astronomy is evolving. Only a few decades ago, we were discovering near-Earth objects with difficulty. Now we're sending spacecraft to intercept them, measuring their composition and structure. What feels mysterious today may feel ordinary tomorrow, not because the universe has changed, but because our instruments have improved. There is also a quiet symmetry here. Oumuamua arrived unexpectedly, passed quickly, and left us with questions we could not fully answer. 1998. KY26, by contrast, is known in advance. Its orbit is charted. Its encounter is planned. We will meet it deliberately. The first visitor surprised us. The next small stone we will greet intentionally. And through that greeting we may learn whether the faint acceleration that puzzled us in 2017 was simply the whisper of hydrogen escaping ancient ice, or whether something even subtler remains to be discovered. Either way, the upcoming flyby is more than a mission detail. It is a bridge between speculation and evidence. It is the moment when a theory about invisible gas trapped inside frozen rock will face direct observation. A small spinning stone drifting quietly, about to be illuminated not just by sunlight, but by curiosity. While discussions of dark comets and hidden hydrogen continued, something grounding happened in late 2019. Another interstellar object appeared. It was discovered by amateur astronomer Gennady Borisov, and soon received the designation 2I Borisov. The 2I simply means it was the second confirmed interstellar object ever observed. Unlike Oumuamua, it did not arrive quietly and ambiguously. It behaved exactly the way astronomers expected a comet to behave. As Borisov approached the sun, it began to glow. A visible coma formed, a diffuse cloud of gas and dust surrounding its nucleus. Sunlight illuminated this expanding envelope, and a tail began to stretch behind it. There was no debate about whether gas was escaping. The evidence was clear in images. Spectroscopic observations detected familiar molecules, including water-related compounds and carbon-based gases, commonly seen in comets from our own solar system. In other words, Borisov looked like a comet. And that was important, because it reminded everyone that not all interstellar visitors need to be strange. Borisov's nucleus was estimated to be roughly half a kilometre across, larger than many estimates for Oumuamua. As it drew closer to the Sun, jets of gas and dust were observed streaming outward. These jets produced measurable non-gravitational acceleration, entirely consistent with standard cometary physics. There was no torque mystery. The rotation and acceleration behaved as expected. The release of material was visible, measurable, and ordinary. Eventually, as Borisov passed through the inner solar system and moved outward again, it began to fragment. Pieces broke off. Its structure weakened under thermal stress. This too is common among comets that experience strong heating for the first time in millions of years. Everything about Borisov fit within the familiar framework of comet behaviour. And that familiarity was reassuring. After years of speculation about Oumuamua's shape, acceleration, and possible exotic origins, Borisov provided contrast. It showed that interstellar objects can be straightforward, composed of ice and dust, responding to sunlight in predictable ways. This contrast reshaped the narrative gently. Instead of asking whether all interstellar objects are unusual, we now ask why these two differed so much. Why did Borisov develop a bright coma, while Oumuamua did not? Why did Borisov's activity produce clear dust signatures, while Oumuamua remained visually silent? One possibility is that their compositions were different. Borisov may have retained more volatile materials near its surface. Perhaps it formed in a colder region of its original star system, preserving ices that responded dramatically to sunlight. Oumuamua, by contrast, may have spent longer drifting through interstellar space. Its surface may have been hardened by radiation. Its volatile materials may have been buried deeper or chemically altered. Or perhaps they were simply different kinds of objects from the beginning, one a traditional comet, the other a fragment shaped by different processes. The key point is this: with only 2 confirmed interstellar objects observed so far, diversity is not surprising. 2 data points do not define a rule, they open a spectrum. Borisov teaches us that some visitors behave exactly as expected. Oumuamua teaches us that others may challenge our categories. Together, they suggest that the galaxy sends us fragments shaped by countless histories. And there is another lesson here as well. Borisov was discovered earlier in its approach than Oumuamua. That earlier detection gave astronomers more time to prepare observations. Telescopes across the world, and even in space, were directed toward it while it was still inbound. As a result, the data collected for Borisov were richer and more complete. Its composition was analysed in detail. Its activity was monitored over months. With Oumuamua, by contrast, we detected it after it had already passed closest to the Sun. Our observational window was short. It was fading even as we began studying it. In a sense, Borisov arrived at the right time, when our survey capabilities were improving, when coordination between observatories was rapid, and it showed us what a well-observed interstellar comet looks like. This is important for balance. When mystery arises in science, there is a natural tendency to lean toward the extraordinary. Headlines amplify unusual interpretations, imagination expands. But Borisov gently restores perspective. It reminds us that the simplest explanations often remain valid. It shows that the laws governing our solar system apply elsewhere. It reassures us that the galaxy is not fundamentally alien in its chemistry. And yet, even with this reassurance, the questions raised by Oumuamua do not disappear. They simply become more specific. Instead of asking, was it alien? We ask, what process shaped it differently from Borisov? Instead of wondering whether it was artificial, we examine how radiation, ice chemistry, and long interstellar exposure might produce diverse outcomes. Borisov does not close the case. It stabilizes it. It allows us to continue the investigation calmly, grounded in evidence. There is something comforting about that. Two visitors from beyond the solar system. One behaved like a comet we already understand. The other behaved like something slightly more subtle, neither overturned physics, neither violated known laws. Both expanded our experience, and somewhere, even now, other fragments are drifting toward us, some perhaps ordinary, some perhaps unusual. We do not know which we will see next, but we are better prepared than we were before. Because of Borisov, we know what familiarity looks like. Because of Oumuamua, we know how to recognize a whisper. Now that we have explored how Oumuamua behaved, its subtle acceleration, its tumbling motion, its possible hidden chemistry, it is natural to ask a quieter question. Where did it come from? When an object passes through the solar system on a hyperbolic path, astronomers can calculate its incoming trajectory. By measuring its speed and direction relative to the Sun, they can determine the general region of the sky from which it approached. For Oumuamua, that incoming direction pointed roughly toward the constellation Lyra, not far from the bright star Vega. This does not mean it came from Vega itself. It only means that, from our perspective, it appeared to arrive from that part of the sky. But tracing an object's origin is not as simple as drawing a straight line backward. Stars move. The Sun moves. The entire galaxy rotates. If we try to rewind the motion of Oumuamua millions of years into the past, we must also rewind the motion of nearby stars. Each star follows its own path through the Milky Way, influenced by the galaxy's gravitational field and by subtle interactions with other stars. Over time, small uncertainties grow. Even tiny errors in velocity measurements, fractions of a kilometre per second, become enormous positional uncertainties when projected backward over millions of years. Imagine trying to follow a leaf backward through decades of shifting wind. You can estimate the general direction it came from, but after enough time, the precise path becomes blurred. Astronomers have attempted this, reconstruction. Using data from star catalogues, particularly those compiled by the Gaia spacecraft, which measures stellar positions and motions with extraordinary precision, they simulated the past motion of nearby stars. Several candidate stars have been proposed as possible origins. Some were relatively close in the distant past, within a few light years of the reconstructed path. Others were more speculative, but none could be confirmed. The problem is not lack of effort. It is the nature of orbital dynamics over vast timescales. As Oumuamua travelled through interstellar space, it likely encountered small gravitational perturbations. Passing stars, molecular clouds, and the overall gravitational field of the galaxy would have nudged it subtly. Each nudge would alter its path slightly. Over tens or hundreds of millions of years, those small deflections accumulate. Even if we could measure its present velocity perfectly, which we cannot, reconstructing its precise origin would require knowing every gravitational influence it experienced along the way. That information is lost. The best we can say is that it arrived with a velocity typical of stars in our galactic neighbourhood. It was not moving unusually fast relative to the local standard of rest, the average motion of stars near the Sun. This suggests that it may have been drifting between stars for a long time, no longer strongly associated with any particular system. It could have been ejected from its home billions of years ago. Perhaps during the chaotic early formation of its parent star system, when giant planets were migrating and gravitational interactions were violent. Such processes are known to eject large numbers of small bodies into interstellar space. Our own solar system likely did the same. In its youth, as Jupiter and Saturn shifted positions, countless icy fragments from the outer regions may have been flung outward, some into distant orbits, some entirely beyond the Sun's gravitational reach. Over billions of years, the Milky Way has become a vast exchange of shards. Stars shed debris, planets scatter comets, fragments drift quietly in the dark. Oumuamua may be one such fragment. Its reddish surface suggests long exposure to cosmic radiation. Its lack of dramatic activity hints at prolonged alteration. Its velocity relative to nearby stars does not point to any obvious recent origin. When astronomers traced its path backward a few million years, they found no definitive parent system. Only possibilities, only overlapping uncertainties. And perhaps that is fitting. There is something almost poetic about an object that cannot be traced to a single star. It becomes less a messenger from one place and more a traveller of deep time. It may have wandered between stars for longer than complex life has existed on Earth. It may have been drifting through the galaxy while our planet was still molten. The age of Earth's oceans is measured in billions of years. Oumuamua could be older still, formed in another system long before our solar system fully settled, and during that immense journey it would have experienced the quiet cold of interstellar space. No sunlight, no warmth, only starlight from distant points, and the steady flux of cosmic radiation. Its surface chemistry would have evolved slowly. Its structure may have hardened, its internal gases may have accumulated. Then, by chance, or by the quiet mathematics of orbital motion, it crossed our path. For a brief moment in cosmic time, it entered our system, warmed, accelerated slightly and departed. We caught it mid-journey, not at its beginning, not at its end, just passing through. The inability to trace its origin precisely is not a failure of science. It is a reminder of scale. When dealing with millions of years and galactic distances, certainty fades gently into probability. We can reconstruct broad trends, we can identify plausible scenarios, but the exact birthplace of a wandering shard may remain unknown. And perhaps that uncertainty is part of its beauty. It arrived without a return address, and in doing so, it invited us to consider the galaxy not as isolated star systems, but as a connected environment, one where fragments travel freely, carrying stories written in ice and radiation. When we imagine the solar system, we often picture something self-contained. A central sun, planets in orderly orbits, comets looping in from distant reservoirs and then returning again. It feels stable, closed, familiar. But on larger scales, the solar system is not an isolated island. It moves around the centre of the Milky Way once every roughly 230 million years. During that long orbit, it passes through different regions of the galaxy, sometimes through denser star fields, sometimes through quieter stretches of space. And just as our system travels, so do countless others. In their early stages, star systems are turbulent places. Giant planets migrate. Gravitational interactions scatter smaller bodies outward. Comets are flung onto distant trajectories. Some are sent into long elliptical orbits. Others gain enough speed to escape entirely. Escape speed is not a dramatic threshold. It is simply the minimum velocity required for an object to overcome the gravitational pull of its star and continue outward indefinitely. For our Sun, at Earth's distance, that speed is about 42 kilometers per second. Farther out, it is lower. When young planets shift and gravitational forces align just right, small icy bodies can cross that threshold. They are cast away, not with intention, but as a natural consequence of orbital dynamics. Over billions of years, every star system likely contributes to a growing population of interstellar debris. Fragments of ice, shards of rock, objects too small to shine on their own, drifting quietly between the stars. The Milky Way, then, is not merely a collection of separate systems. It is a vast exchange network. Stars shed material, planets scatter remnants, and these remnants travel. Imagine trillions upon trillions of small objects moving through the galaxy, most never encountering another star closely enough to be noticed. They drift for millions, perhaps billions, of years. Their surfaces are altered by radiation. Their trajectories are gently nudged by passing gravitational fields. Occasionally, one of them crosses the path of another system. Most likely, many pass through unnoticed. Only recently have our telescopes become sensitive enough to detect such visitors. It is estimated that thousands of interstellar objects may pass within the orbit of Neptune each year. Most are small and faint, far beyond the reach of our instruments. But statistically, the solar system is constantly being traversed by tiny travellers. Oumuamua was not necessarily rare. It was simply the first we clearly identified. This realization changes the emotional tone of the story. Instead of viewing Oumuamua as a singular messenger, we begin to see it as one of many, a shard within a cosmic stream. It may have been wandering for hundreds of millions of years. During that time, it may have passed through interstellar clouds, encountered distant starlight, and felt the faint gravitational tug of stars it never came close enough to see brightly. Its surface chemistry may have evolved slowly under constant cosmic ray bombardment. Water ice could have been altered. Hydrogen molecules may have formed and become trapped. Its outer layers may have hardened into a protective crust. All of this could have happened long before Earth developed complex life. There is something humbling about that. The age of Earth's oceans is measured in billions of years. The age of the solar system itself is about 4.5 billion years. Oumuamua could easily have formed in another system before our planet even existed. It could be older than our continents, older than our atmosphere, a relic from another stellar nursery cast out during planetary upheaval, drifting silently through the galaxy, while civilizations rose and fell on worlds it never saw. When we say it was an interstellar object, we sometimes focus on the distance it travelled, but perhaps we should also consider the time. Time between stars is measured not in years, but in epochs. In that immense span, the galaxy becomes less a collection of isolated systems and more a slowly mixing ocean of debris. Fragments cross boundaries. Material from one star system can, in principle, be captured by another. Though rare, gravitational capture is possible. In the early chaotic phases of star formation, such exchanges may have been more common. It is even conceivable that some material in our own Oort cloud, the distant reservoir of comets surrounding the solar system, originated elsewhere long ago. If so, then we're not merely observing travellers from afar, we may already host them. This perspective softens the mystery. Oumuamua was not necessarily an emissary with intent. It was a participant in a vast ongoing process, the natural redistribution of small body across the galaxy. Its arrival does not imply contact, it implies connection. The Milky Way is not static, it is dynamic. Over billions of years, matter is exchanged, redistributed, scattered, and occasionally captured. And occasionally, for a brief moment, one of these ancient shards passes close enough to be noticed. We measured its speed, about 26 kilometers per second as it departed the sun. We calculated its trajectory. We debated its composition. But behind those numbers lies something quieter. A fragment that may have wandered longer than any structure built by humans has stood. a piece of another system, shaped by radiation and time, crossing our sky for a few weeks before fading into darkness again. When we speak of the galaxy as a shard exchange, we are not invoking drama. We are acknowledging scale. Stars form, planets migrate, debris is ejected, the cycle repeats, and somewhere, even now, countless other fragments are drifting, some toward us, some away from us, most unseen. We were fortunate to notice one, not because it was unique, but because it arrived at a moment when our instruments, our models, and our curiosity were ready. After contemplating the vast exchange of fragments across the galaxy, it is almost inevitable that another thought arises. What if we did not simply watch the next visitor pass? What if we tried to catch one? When Oumuamua was discovered in October of 2017, it was already on its way out. By the time detailed observations began, it was receding from the Sun at roughly 26 kilometers per second, 26,000 meters every second, climbing outward along its hyperbolic path. To intercept something moving that fast, especially after it has already passed, closest approach is extraordinarily difficult, but not impossible. Shortly after its discovery, researchers began exploring a concept known as Project Lyra, a set of mission studies examining whether humanity could, in principle, launch a spacecraft capable of chasing Oumuamua. The challenge begins with speed. To catch up with an object already moving at 26 kilometers per second relative to the Sun, a spacecraft must achieve an even greater velocity, and not just briefly. It must sustain that trajectory for years. Current interplanetary missions reach high speeds using gravitational assists. A spacecraft can fly close to a planet, stealing a tiny bit of that planet's orbital momentum and redirecting it. This technique has been used for decades to send probes to the outer solar system. Project Lyra considered using Jupiter for such an assist, but that alone would not be enough. Another maneuver was proposed, something known as the solar obverse maneuver. The name sounds technical, but the idea can be visualized simply. Imagine diving deep into a gravitational well, falling closer to the Sun than any spacecraft normally would. As the spacecraft approaches the Sun, its speed increases naturally due to gravity. If, at that moment of maximum speed, it fires its engines, the additional energy gained is far greater than if the same burn occurred far from the Sun. It is like swinging on a playground swing. If you pump your legs at the lowest point, when you are moving fastest, you gain more height than if you try to push near the top. The solar obverse maneuver relies on this principle. By performing a propulsion burn near the Sun, where velocity is highest, a spacecraft can achieve a much greater final speed. But diving close to the Sun introduces its own problem: heat. At distances closer than Mercury's orbit, sunlight becomes intense. The thermal environment would require advanced heat shielding, materials capable of withstanding temperatures far beyond those encountered by most spacecraft. The Parker Solar Probe, launched in 2018, has demonstrated that such heat shields are possible. It has travelled closer to the Sun than any previous mission. But Project Lyra would require a carefully timed and powerful burn near perihelion, the point of closest approach to the Sun to gain enough speed. The mission concepts explored launch windows in the early 2030s, between 2030 and 2033. With the right planetary alignments and propulsion technology, it might be possible to intercept Oumuamua in the late 2040s, perhaps around 2048. That is decades from now, and by then, Oumuamua would be far beyond the orbit of Neptune, continuing its quiet journey outward. The technical hurdles are significant. The spacecraft would need a powerful launch vehicle, precise navigation, advanced propulsion, and a heat shield capable of surviving extreme conditions. It would also require careful coordination of gravity assists, perhaps using Earth and Jupiter before the deep solar dive. All of this would be done to chase an object only a few hundred meters across. Some might ask whether such effort is justified, but consider what such a mission would provide. A close-up image, direct measurements of composition, mass determination, surface texture, perhaps even detection of subtle gas release mechanisms. Instead of inferring properties from faint light curves and distant tracking, we would observe directly. We would replace debate with data. Project Lyra remains a conceptual study, not an approved mission. Funding, technology readiness, and political priorities all influence whether such a pursuit becomes reality. Yet even as a concept, it signals something profound. For the first time in human history, we are contemplating intercepting a natural object from another star system. Not to conquer, not to exploit, but to understand. There is something poetic about that. A shard that drifted for millions of years might be met briefly by a machine built by a species that has existed for only a tiny fraction of that time. Two travelers crossing paths, one ancient and silent, one deliberate and curious. Whether or not Project Lyra is ultimately realized, the mere fact that it was studied reveals how quickly astronomy has evolved. In 1998, we discovered small near-Earth objects and struggled to characterize them. In 2017, we identified the first confirmed interstellar visitor. By the early 2030s, we may be capable of planning missions to intercept such objects deliberately. The scale of ambition has expanded, and yet, even as we contemplate chasing Oumuamua, we must remember that others will come. Perhaps slower, perhaps larger, perhaps detected earlier. The next opportunity may be more accessible, and when it arrives, the lessons learned from Project Lyra will guide us. Because once you realize that the galaxy is exchanging fragments constantly, the idea of intercepting one no longer feels impossible, it feels inevitable. While Project Lyra explores the possibility of chasing a visitor already on its way out, another approach is unfolding quietly here on Earth. Instead of racing after the past, we prepare for the future. In 2017, when Oumuamua was discovered, it had already passed its closest point to the Sun. We were late, not by much in human terms, but by enough that we had only weeks of high-quality observation before it faded beyond reach. That timing shaped everything. If we had detected it months earlier, we could have studied it more thoroughly. We might have searched more carefully for hydrogen. We might have refined its mass estimate. We might even have begun preliminary mission planning while it was still inbound. So the lesson was simple: find the next one sooner. And this is where a new generation of observatories enters the story. High in the Chilean Andes, the Vera C. Rubin Observatory is nearing full operation. Its primary mission is called the Legacy Survey of Space and Time. The name sounds technical, but the concept is elegant. The telescope will repeatedly scan the entire visible sky every few nights. Over years, it will build a dynamic map of moving objects, asteroids, comets, variable stars, distant supernovae. Instead of taking occasional snapshots, it will create a living record of motion. This matters deeply for interstellar detection. Small objects entering the solar system move against the background of distant stars. The sooner we notice that motion, the more time we have to respond. With its wide field of view and rapid survey cadence, the Rubin Observatory is expected to detect faint objects earlier and more reliably than previous surveys. Some estimates suggest that once fully operational, it could identify dozens of interstellar objects each year, perhaps even up to 70 per year depending on their size distribution. Not all would be large, many would be tiny, perhaps only a few meters across. But statistically, some will be larger and easier to study. Instead of a single unexpected visitor every few years, we may soon have a steady stream, and with earlier detection comes possibility. If an object is identified months before its closest approach to the Sun, telescopes across the world can coordinate observations in advance. Spectroscopic measurements can begin while it is still inbound. The trajectory can be refined precisely, and if one appears especially promising, large enough, slow enough, mission concepts could move from theory to action. There's also another mission waiting quietly at a gravitational balance point. The European Space Agency is preparing a spacecraft called Comet Interceptor. It will launch and then wait at what is known as the second Lagrange point, a location roughly 1.5 million kilometers from Earth, where gravitational forces from Earth and the Sun balance in a way that allows a spacecraft to maintain a relatively stable position with minimal fuel. From that vantage point, Comet Interceptor will wait for a suitable target. Uniquely, its destination has not yet been chosen. It is designed to intercept a dynamically new comet, one entering the inner solar system for the first time, or, ideally, an interstellar object. This is a different philosophy. Instead of launching toward a known destination, it launches into readiness. It waits, and when a visitor appears, it moves. There is something beautifully patient about that approach. A spacecraft positioned like a listener at the edge of Earth's gravitational influence, ready to respond to whatever fragment drifts inward next. With Rubin scanning the skies and Comet Interceptor poised to depart, the circumstances of the next encounter will likely be very different from 2017. We may see the next Oumuamua while it is still far from the Sun. We may measure its brightness variations earlier, infer its shape more precisely, and search for gas signatures before and after perihelion. We may even launch intercept missions within months if the object's trajectory allows. This shift from surprise to preparation marks a turning point. The first confirmed interstellar visitor caught us off guard. The second confirmed visitor, Borisov, was observed more thoroughly but still without prior warning months in advance. The third, fourth, and fifth may arrive in an era of continuous monitoring. Instead of wondering whether interstellar objects exist, we will begin cataloguing them, studying their compositions, comparing their properties, determining whether dark comets are common or rare, mapping the diversity of fragments drifting between stars, and perhaps, gradually, building a statistical understanding of planetary formation processes across the galaxy. Each object carries clues, not only about its own origin, but about the system that cast it out. The more we observe, the clearer the patterns become, and yet, even as technology advances, the emotional tone remains gentle. We're not preparing for invasion. We're preparing for observation. The sky will not change dramatically. No sudden flood of alien structures will appear. Instead, faint points of light will move slightly differently against the stars, and our instruments, patient, systematic, attentive, will notice. Waiting for the next one is not dramatic. It is simply readiness. Readiness to measure. Readiness to compare. Readiness to learn from whatever fragment happens to cross our path next. And somewhere beyond Neptune, beyond the heliopause where the Sun's influence fades into the interstellar medium, another shard is already on its way. Not intentionally, not purposefully, just following the quiet mathematics of gravity. And this time, we will see it coming. By now, the story of Oumuamua has carried us across many scales, from a faint point of light detected by a telescope in Hawaii, to invisible hydrogen trapped in ancient ice, to gravitational slingshots around Jupiter, to the slow exchange of fragments across the Milky Way. And yet, at its core, the story is not only about physics, it is about curiosity. When Oumuamua passed through our solar system, It did not threaten us. It did not send signals. It did not alter the planet's orbits. It simply moved, fast, quiet, slightly accelerated, before fading back into darkness. We could have treated it as a footnote, a minor astronomical anomaly. Instead, scientists around the world paused and asked questions. Why did it accelerate? What was it made of? Where did it come from? Could we catch the next one? These questions required time, funding, debate, and careful calculation. They led to telescope time allocations, theoretical papers, laboratory experiments on irradiated ice, and mission feasibility studies. All of this effort for an object only a few hundred meters across. Some might ask whether such attention is justified. After all, the world faces immediate challenges: climate, health, infrastructure. Why devote resources to chasing ancient fragments drifting between stars? The answer lies not in utility but in perspective. Curiosity is rarely about immediate return. It is about widening the frame. When we studied Oumuamua, we did more than analyse a rock. We refined our models of cometary physics. We improved our ability to detect subtle non-gravitational forces. We deepened our understanding of radiation chemistry and interstellar ice. We strengthened international coordination among observatories. We began planning missions capable of intercepting objects from other star systems. Each of these advances extends beyond a single visitor. There is also something profoundly human in the act of listening to the cosmos. For most of our species, history, the night sky was static. Stars appeared fixed. The planets wandered slowly. Comets arrived occasionally, dramatic but rare. Now we know that space is more dynamic than it appears. Interstellar objects drift through our solar system routinely. The galaxy is exchanging fragments constantly. The boundary between ours and theirs is porous. Recognizing this does not change our daily lives, but it changes our sense of place. It reminds us that Earth is not isolated. We orbit within a broader environment, a galactic ecosystem where matter moves quietly across vast distances. There is humility in that realization. We did not summon Oumuamua. We didn't predict its arrival decades in advance. We simply noticed it, briefly, and tried to understand. And even after months of study, debates over sails and hydrogen, torque and sublimation, we do not have absolute certainty. Was it a dark comet quietly exhaling trapped gas? Was it an unusually thin fragment pushed gently by sunlight? Was it something we have not yet fully imagined? The data favour natural explanations, but complete resolution remains elusive, and perhaps that is appropriate. Not every mystery must end with a definitive answer. Some end with refined understanding. Some end with better questions. The price of curiosity is not only financial or technical. It is the willingness to accept uncertainty, to live comfortably with incomplete information, to continue observing, measuring, and refining without demanding immediate closure. In this way, science resembles listening more than conquering. We listen for faint accelerations. We listen for subtle spectral signatures. We listen for the quiet drift of distant objects against the stars. And when something unexpected appears, we lean in. We do not panic. We do not assume intent. We examine. We compare. We test. The inevitability of future visitors ensures that this story is not over. Rubin Observatory will scan the skies. Comet Interceptor will wait at the edge of Earth gravitational influence. Perhaps one day a spacecraft will meet an interstellar shard directly, and when that happens, the questions raised in 2017 will echo gently forward. Whether alien or natural, Oumuamua changed astronomy. It transformed a theoretical possibility into observational reality. It reminded us that the galaxy is not distant and abstract. It is active, exchanging material, shaping objects long before we see them. It showed us that even a small deviation, just a few millionths of a meter per second, can open an entirely new line of inquiry. And perhaps most importantly, it invited us to pause, to look upward, to recognise that we inhabit a moving system within a moving galaxy, that fragments from elsewhere can cross our path without warning, that we're capable of noticing. There is no dramatic resolution here, no final revelation, just a widening awareness. Somewhere beyond the heliopause, another shard is already drifting. It does not know we exist. It does not aim for us. It simply follows gravity's quiet curves. And when it enters our sky, whether tomorrow or decades from now, we will see it a little sooner. We will measure it a little more precisely. We will wonder again. And then, as it departs, we will watch it fade, carrying with it the silent reminder that curiosity is not about certainty. It is about attention, about listening carefully to what moves gently in the dark.